Good evening, everyone. My name is David Smrcka. My colleague here is Zdeněk Pucholt, and today we would like to talk to you about our presentation, which is about diesel cycle. Mainly, we worked on a simulation of a diesel cycle, which we want to use for educational purposes. In the first half, my colleague will tell you something about the theory behind the diesel cycle and something about the historical background of this problem. And in the other half, I will tell you about what you all want to know, and that is how we worked it out in Mathematica. So I will just pass the microphone to my colleague.
Okay, so good evening. At first, I would like to speak about theoretical background of diesel cycle. Diesel cycle is thermodynamic cycle which was invented by Rudolf Diesel in 1893. There is his photo. As every thermodynamical cycle, we can create a PV diagram of thermodynamical cycles. There are four important parts of this cycle. This cycle starts in the state number 1. In the state, the gas in the chamber is compressed. We have to do some work, and we move to the state number 2. In there, the fuel is injected into the chamber, and then the fuel is expand, and next part is expansion of this fuel. In the state number 3, there is expansion, and this is a very important part. This is only one part in which the diesel cycle work. And then after that, we are in the state number 4, in which the air and the rest is filled out from this machine. And then we are back in the state number 1. If we return to the theory background, we have to do work in between states number 1 and 2, and work is done between states number 3 and 4. There are two isentropic parts in which heat is not input or output. There is another part how to calculate ideal thermal efficiency of diesel cycle. It depends on many parts, on many parameters. The first one is cutoff ratio. It is a ratio of two volumes, volume number 3, which is there, and volume number 2. It is during the chamber time. Next part is compression ratio. It is marked as a B. It is a ratio of volumes number 1 and 2, and the ratio of specific heat, which is called as a Poisson constant. So there is an equation of ideal thermal efficiency of a diesel cycle. But of course, in practice, the real efficiency is significantly lower due to friction and due to the heat losses. So, next part is for diesel engine. The most important thing is that a diesel engine converts heat into the work. It is used not only in the cars, but in power generations, diesel electric locomotives, and submarines, for example. The highest thermal efficiency of any standard internal or external combustion engine, due to its very high compression ratio and inherent lean, but which facilitates unburned gases to scavenge waste heat. If we create real engine, the efficiency may be about 50%, but usually it is more lower. If we are not so interested in the mass of this engine, Usually we can create a big engine and the efficiency is highest. So there is a picture of how some diesel engine works. And another part of theoretical background is history. There are some important dates of diesel engine. So in 1891, Herbert Stewart invents the first internal combustion engine. And later, in 1892, Rudolf Diesel gave a patent. If you use Wolfram alpha, you can find some information about Rudolf Diesel, a special date of birth, place of birth, and, for example, place of death. It is English Channel. There is his picture, and there is hints per day. You can see this area because we were interested in that. So there is the big peak. So after that, in 1893, it is the date of invention diesel engine. So you can find, using Wolfram alpha, that it is 120 years ago. There is a picture of Rudolf Diesel height compression prototype engine in 1897. Later, this engine was applied not only into some laboratories, but in practice. For example, you can see that it was used for river and canal operations, and for example, in Russia or in France. Later in 1904, the French built the first diesel submarine called the Zit. In 1905, 4 diesel engine turbochargers and intercoolers were manufactured. In 1930, first US diesel power passenger car was constructed, built in Columbus in Indiana in the USA. And the last information, first European passenger cars with diesel engines were constructed by Citroën company. So that's all about theoretical background, and now my colleague described the implementation of diesel cycle in software Mathematica.
Thank you very much, Zdeněk. That was a nice introduction to diesel cycle. Thank you very much. So it's now time to show you how we implemented it in Mathematica. Mathematica is a very powerful tool. It's very reliable, and everyone and it's used by many majors throughout the world. And first thing we did was these 3 diagrams. You have already met the PV diagram in the introduction. Then we have a pressure to temperature diagram, and lastly a temperature to entropy diagram. In the sliders up here, the student that wants to look at these diagrams, he can change the initial volume, initial pressure, and initial temperature that define the starting points that are in here, here, and here. Then just by changing the compression ratio and cutoff ratio, you can see that the efficiency of the cycle and the whole diagrams are changing. The compression ratio is the ratio, it's the initial volume to volume after the piston compresses the air in the cylinder. You can see that the pressure is very high. Also, the temperature is the highest. But it's the isentropic phase, so there is no change in the entropy. After that, it's isobaric phase. Isobaric phase. It's here. No, it's right. It's an isobaric phase. After that, the isentropic. That's the part when the explosion of the fuel, which comes into contact with the hot air, occurs. After that, it's a high. It's fast expansion of the volume of the compressed volume, and this part is the part when the fumes are released from the cylinder. But just constructing these diagrams where the student can change just the compression ratio, cutoff ratio, and initial values, it's not something, it's too easy for Mathematica. Mathematica can do better. So we decided to make it a simulation in time. We constructed these little points, and by the student can run the simulation. And also we applied angular gauges that are already in Mathematica since version 9, because why not? It's much more nicer using these gauges than just having dynamic changing numbers. But I can see that animation is running too fast. I'll try to slow it down a little. Give me a moment. It's getting slower and slower by the time. Or not. This way the student can see the changes in the volume, pressure, and temperature of these cycles. Yeah. So there is a volume, pressure, and temperature. You can see that right now we are in the exhaustion phase. No exhaustion, the phase where the fumes are exhausted from the cylinder. That's the one part. And the final part was to do a 3D model of the cylinder, the piston, where on the right side you can change the diagram you want to watch when the piston is moving. Also, there are the angular gauges that were in the previous part. Yeah. I think you can see that. Just adjust the animation ratio to 3. It should work, hopefully. Let's go. Unfortunately, it seems that the temperature gauge isn't working properly. So the student can watch how the temperature in a phase where the compression occurs changes depending on compression ratios and a cutoff ratio. You can see that when the compression ratio is higher, the temperature of the compressed air is also getting higher, but with increased cutoff ratio, that is this part. The temperature is lower. Also, you can see how it changes in PT diagram and TS diagram. The final thing is that we also compute the overall efficiency of this cycle with these initial temperatures. Okay. So this is the final part of our simulation, and the hardest part was implementing it in Mathematica. The equations were pretty easy, and we hope that in the near future we will make it much more better, including some new features. Thank you for your attention, and do you have any questions? Or what questions do you have? Yes?
Is that 5 or 6 lines of code, is that all that's driving the...
No. It may seem that way, but it's mainly constructed of separate functions for each of the phase. Of each phase, there is this PV diagram moving in time, PT diagram in time, and I can go on and on. Yeah, I find it much more better to do the functions separately and then just in the manipulate to put them together, and the code is much more easier to orientate in. Yeah. Thank you.
You built this simulation
Yes.
to apply in the classroom?
So the question was if this simulation is applied in classroom. Yes, we are working on it, as I said, and we constructed it with the idea, with the purpose to show the students, to make it for students easier to visualize the PV diagrams, how PV, PT, TS, and how it works in the cylinders, because the thermodynamical cycles are not so easy to visualize just without any tools. So yeah. So there is the question.
You mentioned that you have ideas for further development. I'm curious, what are they? What would you like to add?
Yeah. Me personally, I would like to focus more on the 3D model of the cylinder, because it can get better. Also, we can make it some adjustments. As you could see, it wasn't running so fast. The code is really long, and of course some more output data of it would be nice. Yeah. Thank you for a question. So, are there any questions?